If you've ever opened non-text files in a text editor, it's very likely you've come across something similar to this. It's important to understand that even though this originally looks like just random noise, this is directly how the file is encoded by the system. So by modifying this, you are directly modifying the image. My goal was to make a program that can create images as well as load, modify, and then save them by only working on this level. This video is going to cover how these files work and how this was done. It's important to note that this was only done for one specific type of file, that being .bmp files or bitmap files. I chose to work with these because I think they are by far the simplest of the standard image file types and are thus good for purposes here, and there are large similarities between how these are stored and other types like .pngs. Now let's go back to the text visualization of this file, which also is a BMP file and is shown here. So the data here is shown in a form of ASCII. ASCII delegates 1 byte to each character. 1 byte is equivalent to 8 bits or 8 digits in binary. You can imagine this as this form of ASCII having a table of 256 possible characters, which characters in a text file can be. The table of possible characters includes normal characters and control characters. Control characters perform an action like null shown here in the file, but also new line and bell, although for all intents and purposes in this video, they won't be treated differently from the normal characters. When converting ASCII to other forms, think of the index of the character in the table being used instead of anything else. So capital A can be represented by 65. 1 byte can be represented pretty easily in a number system called hexadecimal, which uses base 16 instead of base 10. With only 2 hexadecimal characters, you can make any number between 0 and 255, which allows for 256 representations in total. Representing ASCII characters in hexadecimal is similar as writing a base 10 number in binary. It's the same thing, just written a different way. You can convert ASCII to hexadecimal pretty easily with the basic Python script. Here's the hexadecimal conversion of this file. But how does this hexadecimal represent the actual file? So the way files work is that they have a header and then the actual data. The header gives any reading program general info about the file, like its type or size. There may be multiple headers per file. BMP has a header called the bitmap file header, and then either one called the bitmap info header, or a more modern but much larger and more complicated bitmap v5 header. Technically there could also be a bitmap v4 header, but I never encountered it when making this program. I built up programs that does most of the work for us in terms of translating the hex and then separating the bytes for the parts. Also notice it's a little endian except for the very first part, meaning the smallest byte comes first. So this is like writing 500 as 005 instead of 500. So that's why the bytes are flipped for some of these sections. Out of ease and convention, it separates and flips each byte of 2 hex characters. Let's focus on the first section for now. Notice the first 2 characters are BM. Signature comes first in files and tells the reading program this is a BMP file. For the rest of it, it is much easier to learn about how this part of the file works when viewing the hex contents. Next we have file size, which gives 102 bytes. This is actually what Windows reads to tell us the file size, so this matches. Next are 2 reserved sections which are blank for BMP files. After that we have a parameter for the data offset, which tells us how many bytes until the actual image data is reached. Notice this is the exact amount of bytes until the scanline section is reached, which contains the actual pixel data. The next section, which is bitmap info header in this case, entails general properties of this file. Most of these won't be super important for now, but there are a few notable ones. The width and height parameters give us the pixel width and height of the file. Also important is the bits per pixel parameter, but to understand that we will need to go to the next section. The way pixel data is stored is that horizontal lines are stored from left to right, and also from bottom to top. So scan line 1 is the bottom line of pixels in the image from left to right. So now recall that bits per pixel is 24. This means that the information stored about pixels is stored in 24 bits, or 3 bytes. Now the only information required for this format is the color. Recall a byte or 8 bits can have values from 0 to 255, which means it can store the standard 255 color values. So 3 bytes is enough to store 3 of these, 1 for R, 1 for G, and 1 for B. Now by looking here, you can actually see the pixels represented directly. Also the values, instead of being stored as RGB, are stored as BGR, so blue, green, and then red. So it's flipped. So let's look at scanline 3 for instance, which is referring to the top line of pixels. We can immediately see the fully black first pixel, then a fully red second pixel, and then an orange pixel in third. The remaining bytes are something called padding, which are used so that each scan line rounds out to a multiple of 4 bytes, which is important for computer processing and storage. We already specified that there are only 3 bytes per pixel, and there are 3 pixels per row, so any reading program already knows that only the first 9 bytes of each scan line are useful. Now recall this is 24 bits per pixel. Most services that can modify BMPs or bitmaps can save them as other types. Paint.net, which I mainly use, has 1-bit, 4-bit, 8-bit, and 32-bit in addition to 24-bit, where bit is referring to the number of bits used for each pixel. Now to get the easier one out of the way, 32-bit just adds another byte for transparency for each pixel. But what about 1-bit, 4-bit, and 8-bit? The way these work is pretty interesting, so you may have noticed that bitmap info header has 2 properties at the bottom, one for colors used and one for the number of concordant colors. So what they do is they tell the reading program that there's a fixed set of colors that are used, and then it shows the table of colors. Now instead of actually describing a color value, they can reference an index on this table with their bits. This can massively reduce the file size, but also really limits the amount of colors. 8-bit can have at max 255 entries on the color table, or 255 colors at max. 4-bit can have at max 16 entries on the color table, and 1-bit can have at max just 2 entries on the color table. Also, something to note about 32-bit bitmaps is that they have to use the previously mentioned bitmap v5 header, which is more complicated. Luckily, most of the values for parameters here are constant in the vast majority of cases, and so it doesn't really matter what they do. I have some stuff on screen if you're interested though. Now that is basically all the knowledge that is required to make a BMP editor. Once I made a program that could easily read it, it was pretty simple to make an editor. I first made a function and loaded it in, which essentially took the parameters defined in the file and info headers in a dictionary, and then I stored the scan lines in terms of raw bits in a list. Changing the color of a pixel just means modifying the element in the scan line list. In order to make a new image function, I just need to set the parameters to the size and then just fill it all in with a single color. The most challenging part of making this program was just reconverting the composed version back into the file, but that wasn't that bad either. Once this was done, I could make some basic Python programs using this module I just made and make some pretty cool images. Thanks for watching.